on chip and the key concepts of system on chip, the types of SoCs, SoC design process, SoC design for testability, steps for DFT, design for testability implementations, and tools used for DFT. We have a short review of that. And the boundary scan test, I just want to highlight a few things about the boundary scan test because it has been predominantly used in the field of SoC and the features of SoC, JTAG, and then followed by the role of machine learning in DFT and implementation workflow of the machine learning processes, challenges and limitations. This is the overall outline of the presentation that we are just going to see today. And regarding the system on chip overview, first of all, we'd like to just see the components of architectures of SoC. So we have the central processing unit, the graphics processing unit, memory, input output devices, peripherals, power management system, system interconnects, clock and reset, digital signal processors, and intermodule communications. So for the intermodule communications, we will be using bus architectures, and we are just going to see the AMBA, the Advanced Microcontroller Bus Architecture, in little detail in this. And actually, the term system refers to the presence of multiple modules within its internal framework. As I just mentioned earlier, the presence of multiple modules like the CPU, graphics processing unit, memory, output devices, peripherals, power, as well as the system interconnects, clock and reset, digital signal processors. All these modules are being just integrated to form a system. And this is so-called the system on chip. It has been molded or it has been just manufactured over a single chip. And that is why the name system on chip. So all the components are interconnected via the internal data bus or networks. So you can see the different components here, CPU, GPU. So all these components are actually interconnected via the system interconnect and inter-module communication. So as well as it is being given with the clock and reset also. So in order to maintain the synchronization process in working, it will be just using the clock as well as the reset processes also, wherever it is applicable. And when you see the central processing unit, it is serving as the main component responsible for executing instructions, performing calculations, and controlling the overall system functionality. So it is the all in all. And generally, we can have different cores of the CPUs. And for example, ARM86, that is, and the other internal instruction set architectures can be utilized in this case of CPUs. And when you just see about the graphics processing unit, so it plays a vital role in a SoC system for managing the graphics computations and accelerating image and video processing operations also. And in multimedia applications like the some videos and other video games and everything, and the multimedia application, GPU contributes to improve graphics quality as well as it will provide the smoother visual experience. That is the role of GPUs. And regarding memory, so the SoCs can be using random access memories as well as the read-only memories. The random access memories used for quick accesses of data and instructions, and read-only memory permanently stores firmware and other important system-level instructions. And regarding the input-output devices for the data transmission and communication with external devices, we will be using USB ports, HD multimedia interfaces, HDMI ports, Ethernet interfaces, audio jacks, wireless connectivity options like Bluetooth and Wi-Fi. All these comes under the input-output interfaces. And peripherals. What are the peripheral components? So we will be using the interrupt controllers, serial communication interfaces like UART, SPIs, I2C, and CAN protocols, and timers, analog to digital converters, digital to analog converters, and various other controllers, interrupt controllers we'll be using in the form of peripherals. So the next one is power. The power management components are regulate and optimize the power usages. Regulates and optimize the power usages. effective distribution of power, the power distribution units among the SOC components that will be managed by this power sources. And regarding the system interconnects, um, fabricate or it will be facilitating the data transfer and coordination among the CPU, memory, and other systems, other modules in a smoother way. So it will run in between these modules, and it will just ease the communication processes among these modules in a very smoother way. So generally, we are using this advanced microcontroller bus architectures, AMBA, or network on-chip access or a type of just system interconnects in this SOC modules. So as I said earlier, the processing unit, central processing unit, GPUs, and regarding the DSP, digital signal processor, what is the use of it? So in some cases, we are supposed to have some filtering, modulation, demodulation, compression, decompression, and audio video processing. In those cases, we will be using a digital signal processor, and it will be used for optimized and signal processing tasks like audio and video encoding. And there is another one factor called AI accelerated for higher end applications like machine learning and AI applications specialized for a deep learning task. Generally, it is used for the AI task. We are using the AI accelerators, and it is an optional thing. And if you want, if you are just going to use these things, then you can incorporate in the basic architecture of SOC design. So this is about the on-chip SRAM, embedded DRAMs. So this was actually this, as I told you a moment ago, the high-speed memory uses for caches. So that is the random access memory, and for small data storage, and the ROM read-only memories are used for the long-term memories here. So regarding the bus systems, we are actually having the interconnects called AMBA. So as I told you already, advanced microcontroller bus architecture, which is the specialized type of bus network or the interconnect layer, which has been used with the SOC designs. So here, so this is actually a standard thing which is used for the standard bus architecture, which is used for the interfacing components in SOC. So currently we are using the fifth version or the fifth revision of the AMBA bus structures actually. So it is generated by ARM for high performance ARM processes. It is generated for high performance ARM processes. It actually has three protocols: the Advanced High Performance Bus AHB and Advanced System Bus ASB, and you can see in the figure, as well as Advanced Peripheral Bus APB. So all these three buses can be used, or it can be used as per their requirements. So if for any high performance or any high frequency components, if you are using for those connections of processors and on-chip memories, we will be using the advanced high performance bus, that is AHB. Or if a little lower level of performances, if it is required. In some cases, if we are using the high performances, and we are not very often, if you are not using the high performances, in that case, we will be using the advanced system bus. And the other free applications like other low bandwidth peripherals like GPIOs, general purpose input output registers, timers, UART. For all these things, we will be using the advanced peripheral bus, that is APB. So that is what it is mentioned in the figure. And after the bridge, you can see APB, it is connected to the UART timer, PIO, as well as the keypads. And in the left side of the bridge, you can see AHB or ASP because it is used for high performance applications in some cases. So the next one is the key components. The key components actually deals with the power management. So power management and security features. So power management is very important. Dynamic voltage and frequency scaling, DVFS, for power efficiency and dedicated power domains to enable selective component shutdowns. So what is this selective component shutdown? So if any one of the component is not being used, it will be just moving to the sleep mode or it will be turned off. So literally it is turned off. It is not exactly turning off. Literally it will be just moving to the sleep mode so that we can save the power of just excessive usage of hardware that can be avoided. So that process is be done by the operating system of the SOCs. So here the software part of this SOCs, that is the power optimization procedures. So dynamic voltage and frequency scaling, that is very much utilized for power efficiency, as well as dedicated power domains to enable selective component shutdowns. So that is also incorporated with the SOCs, and that is mentioned as a key component, one of the key components of SOC designs. And the next one is security features. What is the need for security actually? So if you are just transferring the data, then it is highly required for the cryptographic engines, like a high security cryptographic engines. And this AES, I can just highlight this. This is AES. It is the one of the standards, encryption standards that is being utilized in just transferring the data between SOC devices. So here, this AES is actually an acronym of Advanced Encryption Standard. Advanced Encryption Standard, and it has been used by the US government to protect classified informations. And after that, it has been used worldwide, and it has been accepted worldwide, and it has been used worldwide in SOC designs. Okay. So it is actually the AES standards are actually working based on block chippers. So the levels of the encryptions ranges from 12, 10, 12, and 14 blocks or 14 levels of encryptions. Okay. So AES actually uses multiple cryptographic keys, and each of the keys will undergo the multiple rounds of encryptions. So better protects and data and ensure its confidentiality and integrity. To encrypt, to just better ensure the confidentiality and integrity, and we are actually going for this type of encryption cryptographic technologies. So actually, AES encryption works based on three different categories: 128-bit, and actually the key length, that is 128-bit, and 192-bit, as well as 256-bit. So again, let me repeat, it is 128, 192, and 256. So in case if we are using 128-bit, the 10 level or 10 rounds of encryption that will be employed. And if it is 192, 12 rounds of encryption, and it is 256, then it is highly secured, highly encrypted. That is a 14 rounds of encryptions. In earlier days, they have used that DES encryptions. So before AES encryptions, they have used DES encryptions. So DES stands for Data Encryption Standards. Data Encryption Standards. So this data encryption standards has been decoded, and because of this reason, they have just developed the very high cryptographic or high secured AES encryption standards. Okay. So what are the actual